also the constant volume gas thermometer. The thermometric properties respond differently to temperature changes, and therefore we shall expect variations when it comes to reading the fundamental interval or getting the interval for the thermometric property value at the unknown temperature, and then also the property value at the steam point, sorry, the ice point. So moving on, what we have here is still exactly what we're doing here, only that I've chosen to do this in order to compare the two. That not always we shall be dealing with resistance, but we can also deal with another thermometric property. And in this case, we are dealing with the length of the mercury column in reference to the liquid in glass thermometer, where mercury is the thermometric liquid. So here, theta is going to be defined as L theta minus L naught divided by L100 minus L naught multiplied with 100 degrees C. This will lead me to 2.73 minus 2 divided by L theta, sorry, this is 2. This is 8.43 minus 2. L100, 2.73 minus 2, and then multiplied with 100. This gives me, I think, 6.43 divided by 0.73 multiplied with 100, which if you feed in the calculator, $6.43, sorry. Yeah, 6.43 divided by 0.73, and then multiplied with 100 degrees. So here I'm getting a temperature of around 880.82 degrees C. When you try to compare this with the 1020, there's a discrepancy of 139. There's a discrepancy of 139. This is so big, but at least we explained that there will always be discrepancies. As much as in comparison to the example which I've used, it looks quite big. I think I need to cross-check with the values down there. But here it is, the solution for Roman 1, and indeed we have also explained Roman 2. So it is the same procedure, only that we're using different thermometric properties. This one, resistance of the platinum wire, while the other one, length of the mercury column. So, moving on, I want to try and do at least an example on each. Let my producer give you question 4. Give them question 4. Now question 4 is yours to try out. It is similar to what I've just done. They are saying that a particular resistance thermometer has resistance of 30 ohms at the ice point, 41.58 ohms at the steam point, and 34.58 ohms when immersed in a boiling liquid. A constant volume gas thermometer gives readings of 1.33 exponent 5 pascals. So these are pressure readings. 1.821 exponent 5 pascals and 1.528 exponent 5 pascals at the same temperatures. So they're asking us to calculate the temperature at which the liquid is boiling on both the scale, on both the platinum resistance scale and then also the gas thermometer. Calculate the temperature at which the liquid is boiling on the Celsius scale. Again, there is a word missing there, sorry. Now, I think I was missing it all the time. Calculate the temperature at which the liquid is boiling on the Celsius scale of Roman 1 resistance thermometer, Roman 2 gas thermometer. I must apologize. Again, the word Celsius is missing between on and scale in the last statement of the question. But it must be calculate the temperature at which the liquid is boiling on the Celsius scale of the resistance thermometer and the gas thermometer. Now, why am I presenting to you this question? Again, I'm trying to emphasize the fact that the two readings will not be the same. When you go through that calculation, you're going to discover that the value of theta while using the resistance thermometer will be different from the value of theta as calculated on the gas thermometer. So, let me hope that people have written that down. However, I'm interested in doing question 5. My producer, kindly give us question 5. Yes, thank you. So, there it is. My question 5 is reading that the pressure recorded by a constant volume gas thermometer at Kelvin temperature T is given by that. Calculate T if the pressure at the triple point of water is 4.2 exponent 4. Yeah. Now, like I said, in the examples which I'm doing, I've started with fixed points being the ice and steam point, or the lower fixed point and the upper fixed point. Now, my third example, which I'll be doing live, is dealing with a fixed point, which is the triple point of water. And in this case, they're telling me that the pressure at the unknown Kelvin temperature, capital T, is 4.8 exponent 4 newtons per meter squared. However, the pressure at the triple point is 4.2 exponent 4 newtons per meter squared. So the question is, what is T? But we saw that the unknown temperature on the Kelvin scale is defined as T thermometric property at the unknown temperature divided by thermometric property at the triple point multiplied with the value 273.16 Kelvin. So my unknown Kelvin temperature is the value 4.8 exponent 4 divided by 4.2 exponent 4 multiplied with 273.16. So this will give me 4.8 exponent 4 divided by 4.2 exponent 4 multiplied with 273.16 is 312.18 Kelvin. I hope my mathematics is correct. 312.18 Kelvin. So this is an example where I know the thermometric property value at the unknown temperature, and I also know the thermometric property value at the triple point. And specifically, my question is very direct because it is in reference to a constant volume gas thermometer. Therefore, the thermometric property is the pressure exerted by the gas, and hence the units of newtons per meter squared. So this is also another example which we shall come across. And indeed, oftentimes, examiners are setting such questions, attaching 3 marks there, and if you know how to go through this, then it's at a giveaway price. I want to remind my viewers out there that I'm doing this topic specifically to bring the senior fives on board and wake them up that what we are doing, they can also benefit, as much as they assume that they are just started the term and then the pandemic hit the land. So kindly, if you know of any senior fives who are doing physics at this level, tell them to always tune in every Wednesday. In fact, from 3 p.m. to 4 p.m. every week, and also on the weekends. Of course, unless otherwise. If the times are to change still, people who stay tuned in, they will always be having the communications. But at least those are the times. Now, I want to move on and do another rare case, which is also unique and very interesting. You can see I'm trying to build from simple to complex. So my producer kindly give us question 6 for my viewers out there to write down. And in question 6, I have that the resistance of a particular resistance thermometer at the Celsius temperature theta, as measured by a constant volume gas thermometer, is that R is equal to 50 plus 0.17 theta plus 3 exponent 4 minus 4. I hope that people can see that exponent. It is minus 4, 3 exponent negative 4 theta squared. Calculate the temperature as measured on a scale of a resistance thermometer, which corresponds to a temperature of 60 degrees at the gas thermometer. Very beautiful. So kindly write that down. Write that down as I also try to summarize it for you. We are now. Let me first of all interpret this question to the general public out there and to all the people who are following in. Kindly, my producer, bring it back. I want to be sure that everyone has written it down. I want to be behind the screen as I'm trying to interpret it. Now, they are telling us that the resistance of a platinum wire or of a particular resistance thermometer at a certain temperature is related to the temperature that a constant volume gas thermometer will read by that equation. Now the equation of R, by the way, you will add theta on R as a subscript, write it as R theta. I'm going to show it here. The equation of R equals 50 plus 0.17 theta plus 3 exponent minus 4 theta squared is showing us what the resistance of a platinum wire would be for a particular temperature theta that has been measured on the constant volume gas thermometer. In other words, it is relating the relationship between the resistance of a platinum wire and a certain temperature that is read on the constant volume gas thermometer. Now they're asking us, when the constant volume gas thermometer reads 60 degrees, given the relationship of the resistance of the platinum wire and the temperature read by the constant volume gas thermometer, what reading will the resistance thermometer give us this time if the constant volume gas thermometer is reading 60 degrees? Let us come here. We are saying that R theta is defined as 50 plus 0.17 theta plus 3 exponent minus 4 theta squared. Now, we know that the unknown temperature on the Celsius scale of a resistance thermometer is such that theta is R theta minus R naught divided by R 100 minus R naught multiplied with 100 degrees C. Now, when the gas thermometer reads 0 degrees C, what will be the resistance of the platinum wire at the same temperature, R0? According to this definition, it will be the value 50 plus 0.17 multiplied with the temperature of 0 plus 3 exponent minus 4 multiplied with, again, the temperature of 0 squared. So, in other words, they are saying that at the steam point, the resistance of the platinum wire will be 50 ohms. Sorry, at the ice point. Then, what will the resistance be at the steam point? At the steam point, the resistance would be 50 plus 0.17 multiplied with 100 plus 3 exponent minus 4 multiplied with 100 squared. So if memory serves me well, 3 exponent minus 4 multiplied with 100 squared. 100 squared is 1 exponent 4. From the law of indices, this leaves me with 3. I shift this twice. This is 17, then plus 3. That gives me 20, then plus 50. So the resistance at 100 is 70 degrees C. Ohms, forgive me. Then, when so I hope that people are following me. This is what I've summarized. The resistance of the platinum wire at a certain temperature as measured on the gas thermometer is given by this relationship. And as we've seen in our question, I've already mentioned that they're asking us what will be the value of the unknown temperature of a certain liquid or substance for which the constant volume gas thermometer has read a temperature of 60 degrees C. And I said that in order to do that, we must first of all remember that the unknown temperature on the Celsius scale of a resistance thermometer is defined like this. However, we're now having a task. What is the resistance at 0? This is unknown, this is unknown, and also this is unknown. But using this equation, we're going to find them. Why? Because this equation is giving us the relationship between the resistance. You can imagine, I have my substance here. It is maybe a liquid. I dip in the constant volume gas thermometer. It reads 0 degrees C. But this equation is telling me that for this temperature, if I was to dip here a platinum resistance thermometer, the resistance of the coil would be 50 ohms. Then, if I transfer now and I immerse this in steam, yes, the constant volume gas thermometer will give me a reading of 100 degrees C. But the resistance of the platinum wire at this particular temperature will be 70 ohms, as calculated using this equation. Then, in the other liquid, whose temperature we are trying to establish, while using the constant volume gas thermometer, it reads 60 degrees C. Now, our question is, what will the platinum resistance thermometer read? But before we attempt to calculate the reading of the platinum resistance thermometer, we must first of all know the resistance of the platinum wire at that temperature, as measured on the gas thermometer. And this is what I'm calculating now. So we have 60 squared multiplied with 3 exponent minus 4. That is giving me 1.08. 1.08 plus 50, that gives me 51.08. Then 0.17 multiplied with 60, that gives me 10.2. Uh, 10.2 plus 51.08, that is 61.28. I hope that my mathematics is correct. I'm using the non-scientific calculator, 50 plus, let me rearrange it just to be sure, 0.17 multiplied with 60, then 3 exponent 2, minus 4 multiplied with 60 squared is 1.08. So 1.08 plus 60.2, yeah, 61.28. So the resistance is 61.28 ohms. So this is the resistance of the platinum wire corresponding to the temperature reading of 60 degrees C as measured by the gas thermometer. Now, what will be the reading of the platinum resistance thermometer? Reading of the platinum resistance thermometer. So, for the platinum resistance thermometer, when the constant volume gas thermometer has read 60, for it, it will read the value 61.28 minus 50 divided by 70 minus 50 multiplied with 100. So this is 11.28 divided by 20 multiplied by 100. So we are seeing that the platinum resistance thermometer would rather read 56.4 degrees C. That is what we have. Now, this is the last form of the questions which I'm quite sure that many of you will come across most of the reference books that we're using, past papers, and indeed the question bank. If it comes and it happens to be outside this, trust me, it will still again require you to employ the knowledge which I've shared with you during these 4 or 3 examples that I've done on the board. I want to beg my producer to give you an assignment, share with you number 7. This one is yours. You're going to go on and try it out. Kindly share with our viewers question 7. The value of property X of a certain substance is given by that. Where T is the temperature measured on the gas thermometer scale, what will be the Celsius temperature at 50 degrees on this thermometer scale? So, it is again the same thing, but maybe the uniqueness in it, which people will enjoy, is that for the thermometric property values at the different temperatures, as I've tried to establish here, 0 degrees, 100 degrees, and then in this case 50 degrees, we shall be remaining with the term x naught because it's a constant. So, I'm saying that when you when you go to T equals 0 degrees, you're going to discover that X naught will be X naught. That is if we go by the mathematics rule of substituting for T is equal to 0. We're going to remain with X naught because the other ones will die or they will disappear. Any number times 0 is 0. They will vanish. Then, when we substitute for T equals 100, we're going to have a certain value, but plus X naught. When we substitute for T equals 50 degrees, again we're going to have a certain value plus X naught. When you try and substitute in this, you're going to have an X naught remaining, but which can cancel out. So, I hope that my viewers out there, you can really get to enjoy this, and then you can go on and even look for more examples. I'm not going to do that, but it is just to try out, and I know that you will really enjoy it. So, maybe my producer also give them the other numbers. Now, question 8, 9, and 10. Question 8 and 9. They are familiar to the other examples which I've already talked about, but these are yours for more practice. Resistance of the element in a platinum resistance thermometer is that at the triple point of water and that at room temperature. What is the temperature of the room on a scale of the resistance thermometer? State one assumption that you have made. A particular constant volume gas thermometer registers the pressure of that at the triple point of water and the pressure of that at the boiling point of a liquid. What is the boiling point of the liquid according to this thermometer? Kindly, if there are some few words which are missing, fix them in order to have the question rhyming with the science. You will forgive my presentation in form of the writing and grammar. I can see there are a few words missing, art, seditious, but I know, us being scientists, we shall be able to fix that. So, as you're writing that down, I'd like to use my remaining time to talk about the other type of thermometer, which is the thermocouple thermometer. And I mentioned that this type of thermometer, for it uses the thermoelectric EMF generated between two junctions as its thermometric property. When you try and read about the details of that statement, in science, that is what we call the Seebeck effect. Now, what is the Seebeck effect about? Experiments show that, indeed, this one we can do in the lab. I'm talking about the thermoelectric thermometer, also known as a thermocouple thermometer. And I'm saying that the principle of this is what we call the Seebeck effect. And I was trying to Seebeck, one word, sorry, because I know that people will go on and try and search this on the internet, but also Tom Duncan talks about it. Now, this is what the Seebeck effect is about. If I get two containers in the lab, and in one of them, I put an ice water mixture, what, according to the mode of operation of this thermometer, we shall be calling the cold junction or the refresh junction. And then, in the other, I put a liquid which is at a temperature which is maybe even above the room temperature. So, according to the mode of operation of this type of thermometer, This one I'll be calling the test junction or the hot junction. Some people call it the hot junction. I've said that this one we refer to as the reference junction or what we call the test junction. Now, if I get two wires of different conductivity, for example, if I get copper and iron, if I get those two wires and I join them together, observations show that if I happen to connect a galvanometer at such a point, the galvanometer is going to give me a deflection. What does that mean? It means that if we have two wires which are maintained at different temperatures, an EMF is generated across the wires. The Seebeck effect helps us explain the origin of this EMF. Now, what is happening? I want us to study this to detail. Because these two are conductors, and at this end, they have been immersed in a hot liquid. You can think of boiling water here. And then at the other end, they are in an ice water mixture. It means that the kinetic energy of the electrons at this point is higher compared to this point. Why? Because we know the kinetic energy is directly proportional to temperature. However, electrons are going to start drifting from this end to the other end across the copper wire. Now, why is it across the copper wire? And I want people to listen to me, by the way, very carefully on this, because it's a very interesting theory. And I would like to share with you the mode of operation of this thermometer and indeed the origin of the Seebeck effect within the shortest time possible. Electrons are going to start drifting. Why in the copper? Copper is of higher conductivity compared to the iron. So these electrons in the copper appear to be more delocalized compared to those in the iron. Now they will start moving from this end and then coming to this end. As a result, at this point, we're going to have an excess of electrons. And at this point, we're going to have a deficit of electrons because they have been transferred to this other end. Now this will seemingly become a positive terminal, and then this will seemingly become a negative terminal. What does this mean? This means that there is a PD now which has been developed across the two junctions. And the development of a positive sign here and a negative sign here is going to cause the electrons to further be attracted to come to this side of the positive potential through now the piece of wire which is made out of iron. Of course, from the elementary science that we know from O level to do with convectional currents, whenever you have electrons drifting from one end to another, it means that there is a current which is flowing in the opposite direction. And this is what gives birth to the thermocouple thermometer. That if I can manage to calibrate this galvanometer or voltage reading instrument, if I can manage to calibrate this by using a certain equation that is showing the relationship of the EMF generated in this arrangement in terms of the temperature difference, then it means that this can start behaving like a thermometer. Because we are seeing that if you have two wires of different conductivity and you maintain one of them at a different temperature and then you maintain the other at a higher temperature, always an EMF will be generated across the wires as explained using the Seebeck effect. I've tried to mention the origin of that EMF, that electrons at the hot junction in the higher conductivity material will become delocalized and then they will start moving to the other end. In the process, this junction is going to become electron deficient, therefore acquiring a positive sign. And then this side where the electrons are collecting is going to acquire a negative sign. somehow a PD will now be developed across these two junctions, which can be read by the galvanometer. And that is what we are saying, the thermoelectric EMF. We shall be calling that a thermoelectric EMF. Now, these values are usually small. Why? Depending on the nature of the materials that we have used, number two, their thickness, and then also the temperature difference. That is why we use a very sensitive reading instrument, which is usually the galvanometer, in order to try and establish the value of those potential drops. So, next time, I'm going to leave this as an assignment for you. Go and then look at the procedure for establishing the unknown temperature on the Celsius scale using the thermocouple, establishing the unknown temperature on the Kelvin scale, again using the thermocouple. Look at the advantages and then also the disadvantages. I know these you will be in position to get online and also from the different reference books. Kindly download the app, let us meet there, and then further this discussion. Otherwise, for today, this is what I had for you, and I would like to congratulate you all for following us every weekday. May the good Lord bless you, and I sign out.
Somera mu Ddiiro lyo ng'ewagiddwa Maryland High School erisangibwa Entebbe. Ssomero ly'abawala n'abalenzi tusomesa arts and sciences okuviira ddala ku siniya esooka okutuukira ddala ku siniya ey'omukaaga nga lisangibwa mu kifo ekiweweevu obulungi. Tulina ebisuula eby'omulembe, science laboratory ssaako ne computer lab wamu ne bw'osomeseza omwana wo mu masomero ga Giant Schools omuli kampasi y'e Bombo Kalule n'ey'e Kabalagala toba na bweraliikirivu bwonna olw'omusingi okutambuzibwa ebyenjigiriza n'ensoma y'abayizi ey'omulembe. Mu masomero gaffe gano gonna tusomesa arts and sciences